Hi, I'm Arpith, and today I'm going to talk on the topic of improving the read performance of big data applications using melted pages. Modern SSDs can store multiple bits per transistor, which enable it to have higher storage capacities. Low cost per bit of such SSDs have made it a commercial success. However, they suffer from longer latencies to read data, resulting in reduced throughputs when compared to flash memories that store single bit per cell. In this paper, we propose a solution which combines various page types in a word line to a single logical page called a melded page. It uses the knowledge of I/O patterns of the workload to improve the read performance of NAND-based solid-state drives by mitigating the overheads involved in the read operation. Before we dig deeper into melded pages, let me quickly walk you through the background knowledge required to understand this presentation. A typical SSD contains a number of NAND flash packages in the device. Each flash package contains multiple dies, which is the smallest unit that can independently execute commands. Each die contains multiple planes, which is the smallest unit that can serve an I/O request in parallel. A plane contains multiple blocks, which is the smallest unit that can be erased. Each block contains multiple pages, which is the smallest unit that can be read or programmed. A page is made up of multiple transistors, also known as cells. The figure here sketches the cross-section of a basic floating gate transistor. Flash memory works by adding or removing electrons to and from a floating gate. A floating gate transistors can be in two states represented here by state 0 or state 1, depending upon whether or not a floating gate is charged or uncharged. With the presence of charge in the floating gate, the minimum gate to source voltage required to turn on the transistor increases. There can be slight variations in the final threshold voltage while programming multiple flash cells to the same state. Thus, each state is represented by a voltage window instead of a definite value. This figure illustrates the threshold voltage distribution of an SLC NAND flash. Here, the y-axis shows the probability density of each state across all transistors. Now, to read the data present in the transistor, a read reference voltage of V0 is applied to the control gate of the transistor. Since our amplifiers in the circuit then check for channel conductivity. If the channel is conductive at this voltage, the bit stored in the cell is inferred to be 1, otherwise it is inferred as a 0. The number of threshold states determines how many bits a transistor can store. 4 threshold states can store 2 bits of data and 8 threshold states can store 3 bits of data. In MLC flash, sense amplifiers test for conductivity at a read reference voltage of V1. If the cell is conductive, then the value held by the cell is inferred to be 1, else it is 0. To read an MSB page, 2 read reference voltages are required. If the channel is conductive or non-conductive at both V0 and V2, then the MSB is interpreted as a 1, otherwise it is a 0. To read the least significant bit in a TLC, read reference voltage of V3 is applied to the control gate of the transistor. Sense amplifiers in the circuit then check the channel conductivity. If the channel is conductive at this voltage, the least significant bit stored in a cell is inferred to be 1, otherwise it is inferred to be a 0. Center significant bit is read by applying 2 read reference voltages of V1 and V5. If the channel is conductive or non-conductive at both V0 and V5, then the value of CSB is interpreted as 1, otherwise it is a 0. Reading the value of MSB from a TLC requires 4 reference voltages indicated by V0, V2, V4 and V6. Individually applying read voltages to the gate of each transistor is infeasible. To reduce this complexity, the control gates of multiple cells are connected to the same line, and this is called a word line. Due to this design, all cells in the page share a common read reference voltage during reads. Hence, all reads to and from an SSD are performed at the granularity of a page. In a nutshell, a page is the smallest unit that can be read or programmed into an SSD. In case of TLCs with 2-3 bits per cell, the LSB of cells in a word line are combined to form an LSB page. All CSBs in the word line are combined to form a CSB page, and the same applies to an MSB page too. The table here shows the latencies to read different page types from a triple level cell. It takes approximately 58 microseconds to read an LSB page, 78 microseconds to read a CSB page, and 107 microseconds to read an MSB page. Ideally, one would expect the latency to read an LSB page to be 4 times lesser than that of an MSB page and 2 times lesser for a CSB page. However, this is not observed in practice due to overheads involved in the read operation. When a read request arrives via the host interface, the controller needs to determine the physical address of the requested data in the underlying flash memory. To do this, it maintains a flash translation table to manage the mappings from logical address to physical addresses. This process of mapping adds to the read latency. The controller then sends this address along with the read command to the control unit in the flash chip. Block and page decoders are used to access the correct word line. However, before reading the data from the selected word line, all other word lines in the selected block are made conductive. This setup operation is required because sense amplifiers are connected to the selected cells on a shared bit line. A voltage greater than the maximum threshold voltage of the transistor, called a pass-through voltage, is applied to the unselected cells to ensure that they are conductive. The conductivity of the selected cell can only be determined after the setup operation. This adds to the read overheads. After the page is read, the controller may also choose to perform various post-processing operations, such as detecting and correcting bit errors. This again adds to the read latencies. Our work mitigates these overheads. Assuming X denotes the latency due to the overheads involved in accessing a page, and Y is the amount of time to apply a read reference voltage and test the conductivity of a cell, to read an LSB page, which requires only one read reference voltage, the latency can be approximated to X plus Y. Similarly, the latency to read a CSB page, which requires two read reference voltages, can be approximated to X plus 2Y. Reading an MSB page from a TLC flash requires 4 reference voltages, and hence the latency can be approximated to X plus 4Y. The total time to read all 3 pages will hence be X plus 7Y. Our approach to alleviate the effects of read overheads involves combining the LSB, CSB, and MSB pages in a word line into a single larger page called a melded page. When a read request arrives, the entire melded page is read in one command. The latency to read the entire melded page reduces from 3x plus 7y to x plus 7y. In this work, we approximate the value of x to be about 40 microseconds and y to be about 18 microseconds. The table here shows the latency to read different page types. Our scheduling algorithm schedules the writes in such a way that later, while reading, requests for data in LSB, CSB, and MSB pages are all present in the read request queue. Now, let us look at why scheduling the writes is important with a simple example. Assume that we have request 0 and request 1 in the write request queue, and assume that we know in advance that the contents of request 0 will be read by a program in the future. This makes it a good candidate to be put in the melded pages like so. If we program all pages in a melded pages in one shot, it becomes susceptible to cell-to-cell interference. It is a scenario where programming all bits in the flash cell present in this word line results in a significant threshold shift in the adjacent cells, thereby corrupting it. So in this example, writing word line 1 will corrupt the contents of word line 0. To prevent this, pages are programmed in shadow programming sequence, which is the zigzag pattern of writing data into the block. However, this process of programming may prevent data when requested later during the read operation to be in the same melded page. Now, reading the entire melded page when only a part of it is used to fulfill the read request has a negative impact on the read performance. To prevent this, the scheduler rearranges the order in which stripe data is pipelined for writes in a manner which compensates for the change in order due to shadow program sequence. So, in this example, after writing stripe 0, we program stripe 3 to ensure that stripe 1 is in the same word line as stripe 0, and so on. Such reordering of writes by the scheduler ensures that later, during reads, requests for the data present in LSB, CSB, and MSB pages are guaranteed to be present in the read request queue. Due to SSD's ability to compute operations in parallel, it is only beneficial to use melded pages when a large amount of data needs to be read. But how large is large enough? Let's take an example of an SSD with 8 channel, and each channel having 8 parallel units and having an operating frequency of 800 megatransfers per second. The page size is 4 KB. For a given size of read request from the host, we measure the time to complete each read operation. For this configuration, we start seeing performance improvements only when the size of data that needs to be read is greater than 2 MB. This is because small reads have better throughput if the pages that hold the requested data is placed in different parallel units, as opposed to melding them on the same die or a plane. Requests that are served from pages on parallel units in different channels show the best performance. Now the problem is, decision to use melded pages needs to be done in a program phase, that is, while writing data. How does the scheduler know the read pattern during the program phase? Well, the host needs to provide the hints to the scheduler when submitting the write request. This can be done using NVMe's directive support. It provides us with an ability to exchange extra metadata in the headers of ordinary NVMe commands. The proposal is to add a new directive that enables the application to declare the read patterns. These hints can be explicitly provided to the developer or automatically generated by looking at the history. Now, given that melded pages are useful only when large amounts of data is read, the question is, where would this be actually useful? Hadoop and Spark are popular open source cluster computing frameworks used for big data analytics and large-scale data processing. One of the most popular distributed data storage systems to manage large data sets is Hadoop Distributed File Systems. HDFS essentially contains the name nodes, which manages the metadata, and data nodes, which stores the data itself. When you store a file in HDFS, the system breaks it down into a set of individual blocks and stores the blocks and various data nodes in the Hadoop cluster. In HDFS, block size by default is 128 MB. To read a file, HDFS clients first request the name node for the list of data nodes that host replicas or blocks of the file. The client then contacts the data node directly and requests the transfer of the desired block. But why large block size? HDFS is designed to store files in a petabyte scale. Having large block size reduces the number of metadata that the name node needs to handle. Also, HDFS clients needs to contact the name node to request the address of the block in the data node. Large block size reduces the number of requests that a client needs to make to access the entire file. For example, if a block size of 4 KB is used to access a 1 TB file, the client will have to raise 2 million requests to the name node. This number is reduced to about 8,000 if a block size is 128 MB. This considerably reduces the network overhead. Since HDFS performs all write and read operations in large chunks and in a sequential manner, the scheduler can predict the sequential read pattern and rearrange write requests to guarantee that later, all requests for data present in LSB, CSB, and MSB pages are present in the read request queue. For the purposes of evaluation, we run Hadoop version 2.9 with Hadoop Distributed File Systems. The workload used does not matter since the I/O pattern of reads and writes from the perspective of the host is consistently sequential due to large block sizes used in HDFS. For our simulation environment, we use simple SSD and implement melded pages on top of it. The table here summarizes the configurations of the SSDs that we use. We vary the page size and the channel's operating frequency. The result for an SSD with 8 channels and 8 parallel units per channel is tabulated here. We observe a performance improvement of up to 45%. As it can be seen in the first column here, as the page size increases, the channel speed becomes a bottleneck. To get around this, we can either increase the operating frequency or increase the number of bits per transfer, which is shown in other columns here. We can also reduce the number of parallel units that share a channel. Here are the results for an SSD with 16 channels and 4 parallel units per channel. To conclude, we propose the use of melded pages to improve the read performance of workloads that read large amount of data in a predictable manner. For workloads that use distributed file systems, we can improve the read performance by up to 45%. If you have any questions, feel free to contact the authors of this paper. Thank you.